The following seminar is organized by the IIT Guwahati SPE student chapter as part of the BATON Technical Series. This initiative aims to promote knowledge exchange in emerging energy technologies and sustainable engineering solutions. Today's session features Professor Surendra Kumar Martha, Professor, Department of Chemistry, IIT Hyderabad, who will speak on Towards Sustainable Lithium-Ion Batteries, Advances in Low and Zero-Cobalt Electrode Materials. This seminar is intended to support academic learning, research engagement and professional development in the field of advanced energy storage systems.
I'll give a roadmap for the lithium-ion battery technologies. I'll give what is the contribution of Indians also in the lithium-ion in this technologies. Pure lithium is not used in lithium-ion cell, because lithium can cause dendrite and can pass through the separator, then can cause safety issues. Lithium has highest energy density and capacity, and weight is less. That's why lithium batteries are emerged significantly. This is the real lithium-ion cell. What is not used in your cell phone? It is like maybe part of it is used in your cell phone actually. This is what real cathode used in a lithium-ion cell. This is the real anode used in lithium-ion cell.
I, Chitra Sharma, officer of this SPE student chapter, welcome you all to today's seminar entitled Towards Sustainable Lithium-Ion Batteries, Advances in Low and Zero-Cobalt Electrode Materials under the BATON Technical Series. We are delighted to have students, researchers, faculty members and industrial professionals with us joining today for this important discussion on sustainable energy storage technologies. It is a distinct honor to have with us our respected head of the department. May I now please request you, sir, to please grace the podium and address the audience.
Today morning, we are happy to see here Professor S. Martha from IIT Hyderabad. Okay, and I think he has accepted the request to give the presentation here on his research field, especially in sustainable lithium-ion batteries, which is advances in stage now by Professor Martha. And also I welcome all of you along with Professor Martha's classmate, and I heard that Professor they are from our chemistry department. So I am happy to see you here, sir. And also from the SPE, society, it is a nice initiative to take this, lecture, knowledge from eminent persons from different IITs, even different, institutions. In this regard, I am really happy to see such type of, lectures. So it will be very nice to hear from you this knowledge that lithium-ion batteries, which is in advanced stage. So I once again welcome you for this lecture. Thank you. I again congratulate to SPE society to organize this nice topics, discussion and lecture. Thank you.
Our chapter serves to create a vibrant platform that broadens the opportunities for students through technical, professional, and community-oriented activities. By organizing lectures, workshops, and expert innovations, the chapter aims to bridge the gap between academic research and real-world energy challenges, especially in the emerging areas such as energy transition, sustainable technologies, carbon management, and advanced materials. The BATON Technical Series is one of such an initiative that promotes the exchange of knowledge between leaders researchers, and academic communities, enabling a meaningful discussion on technologies that would be shaping our dear future. Today, he will be delivering a lecture on sustainable lithium-ion batteries, advances in low and zero cobalt electrode materials. So let's please welcome with a huge round of applause to our speakers.
For inviting me to this seminar at the Department of Chemical Engineering at IIT Guwahati. It's a great pleasure for me to be here, even though I have a small, long association with this institute. My brother graduated in the year 2006 with Professor Bora in mathematics, who is a professor also in IIT Ropar. And I have several friends in chemistry. My batchmate, Professor Aditya, is here. So, which I think we met in between, but this was a long time meet after 30 years even though we know each other. Anyway, thank you again. So, as we discussed, it will be very interactive. You can ask me any questions. So, I should deliver some, not only the fundamentals to some extent, but also I'll give some insight so that you can do research if you are interested in these aspects. So before going to today's presentation, just want to tell what we do at IIT Hyderabad. So basically, we are a material electrochemistry actually. So we can do any electrochemistry, but we don't do all electrochemistry. Correct? We do only for the energy storage systems, especially we started with lead acid batteries. You heard every houses or every vehicle use a battery that is lead acid battery. We extended to lead carbon ultra capacitors. Then our major backbone is development of cathodes and anodes for lithium-ion batteries. We extend this one to sodium-ion batteries, and then we have develop a concept, dual carbon batteries, that's I'm going to talk, and then we work also supercapacitor and recycling lithium-ion batteries. So the goal all the time is to improve the energy density. What is energy? See, it's written the voltage. You can increase the voltage of the cell, or you can increase the capacity, the charge storage. Okay, IT, it is for battery it is called ampere hour, and into the voltage, that is watt hour. Voltage current will give you watt hour, and you divide by weight, it is the energy density. Okay, so to me always energy density is like how long you can drive your vehicle, and power density is how fast you can drive your vehicle. Okay, so today what I'm going to speak, as the title says, I'll give a roadmap for the lithium-ion battery technologies. I'll give what is the contribution of Indians also in the lithium-ion in these technologies, and we'll be talking about the high energy density lithium-ion batteries, how we can develop, and especially we'll be talking about low cobalt to less cobalt based cathodes, but particularly this called nickel manganese cobalt oxide cathodes. We'll be talking about no cobalt, that's cobalt less cathodes. This is the LNMO, lithium nickel manganese oxide, and lithium manganese iron phosphate cathodes. Then I'll be talking about all carbon batteries. Okay, these are actually individual talks, a PhD thesis in all aspects. So I have shortcut in like a few slides for each section. So let me, as it's a student's oriented talk, I just thought to give a small brief. You see, that is this Alessandro Volta, who gave idea of a fast electrochemical cell using copper, zinc place, and stack alternately using a brine cloth solution, and you get a 0.76 volt, and he was showing, you see current generation to Volta in 1801. And today we use the same concept of making batteries, correct? Only battery chemistry have been changed. See, this is a battery pack what is used in your Nexon or in Tata vehicles or Mahindra vehicles, or even this is a Chevy Bolt, is a Chevrolet Bolt, which is a 60 kilowatt hour battery pack. Capacity is 60 kilowatt hour, and the voltage you see 350 volt, and then it weighs about 430 kilogram, and it can drive 500 kilometers around, and it consists of a chemistry called lithium, nickel, manganese, cobalt oxide. He was using copper, zinc. Here, this is the cathode, and graphite is the anode, and use non-aqueous electrolytes. He was using aqueous electrolyte. That is the difference. And here, hundreds of cells are connected in series or parallel to get this battery stack. Okay, so you can ask, why lithium? Correct? You all, today I have not put the electrochemical series. If you see electrochemical series, at the bottom, which element is there? Lithium. Okay, it has potential of 3.04 volt. It always want to oxidize. On the top, you have fluorine. If you can combine, you can get a lithium fluorine cell. But why then? And you can get 6 volt. Why it doesn't exist today? Because you don't have a good electrolyte operating at such high potentials. Lithium-ion batteries are operated at 4.3 volt today. Correct? So limited by your electrolyte fast. Later it is cathode. Okay, so lithium has a highest voltage. If you combine anything with lithium, you will get a good voltage. 96,500 divided by 3,600, that is 1 hour, you can get 26.8. So the rule is that 1 gram equivalent of material will deliver 26.8 H. So that means if you calculate, you have a divided by 6.94 gram per mole into 1 electron. Lithium can give you 1 electron. It can deliver 3,860 milliampere hour. Okay, that means close to 4 ampere hour. But so that means, remember, 1 gram of lithium can deliver 4 ampere hour. In your lithium-ion cell, which you are using in cell phone, which is 20 gram, then why not not 1 gram? Then what is used there? There is something else. Pure lithium is not used in lithium-ion cell. Because lithium can cause dendrite and can pass through the separator, so and then can cause safety issues. I'll come to some extent. So lithium can deliver 4 ampere hour, close to 4 ampere hour. Voltage is high, capacity is high, energy is high, and lightweight. How much? 6.94 gram per mole. What is lead? 207 gram per mole. Correct? Lead acid battery. What is the energy density? 30 watt per kilogram. Because the lead itself is 207 gram per mole and the lead dioxide is 239 gram per mole. Then comes nickel betterite batteries, the AA cells, AAA rechargeable cells, what you are using or Toyota Prius is using, that is nickel metal hydride. Nickel metal, they are a beautiful system, very safe system, but unfortunately because of lithium-ion batteries emergence in 1990, these batteries cannot come up actually. So lithium-ion battery today energy density is 250 watt hour per kilogram. Okay, and the lithium has high voltage, high capacity, less weight, less cell discharge. That's why it's very important. And if you see other elements in the periodic table, electrochemical series, after lithium, you'll have sodium, you'll have calcium, you'll have sodium is around 2.71. You have also calcium, which is about 2.91. You have also aluminum, which is 1.67. Zinc is 0.076. But so lithium is not abundant. So that's how people are thinking of other elements like sodium. Sodium can emerge after lithium, in a few years' time. Wherever the other bivalent or trivalent like aluminum, magnesium, this may take some time. See, because you know that a small element, it's a movement of ions between the cathode and anode. So a bulky ion versus a small cation, correct? Which can move very fast. The dynamics is also very important. We have computational guys present here, so they can tell, so lithium the dynamics will be much faster compared to your magnesium or calcium. So anyway, I do not want to divert the topic. So lithium has highest energy density and capacity and the weight is less. That's why lithium batteries emerge significantly. So if you see today, it has an application not in your cell phones, implanted devices. Today we have EVs and grids even. And if you look, our government targets 30% EVs on the road by 2030. That's why you see a lot of vehicles today on the road actually. And Mahindra and Tata are the leading players. And BYD also coming up. BYD is trying to enter from China, and somehow the Indian government is trying to stop it. Because if we want to have our own technology, will be used in this vehicle actually. And unfortunately, not a single battery is produced today in India. Okay, it's all imported from elsewhere. So we have also a two-wheeler company, in next to IIT Hyderabad is a startup from, no more a startup, it's a 10-year company from IIT Hyderabad, spin out from IIT Hyderabad. So it's a mechanical engineer. So they have e-Pluto vehicles by pure EV. So I do have a electric vehicle program where the goal is to develop 5 ampere or 30 ampere cells. I have a small module of exact 5 ampere cell what I am holding here. So this was started in 2019, and the program halted because of COVID and many other issues. Unfortunately, I lost a lot of money. And then this is the real lithium-ion cell, what is not used in your cell phone. It is like maybe part of it is used in your cell phone actually. So it consists of a lot of cathodes, anodes. In between you have separator. This is I'll show you when I have this is a sodium-ion cell what we develop in our lab actually. So this has like 20-30 layers of sodium. Okay, I'll come to that. Not to worry at all. I'll spend some time here. This is a very important slide. So just wanted to tell you how lithium-ion battery have evolved to some extent, and how the Indians have a contribution to lithium-ion battery. So Professor Whittingham in 1976, when he was working in ExxonMobil, so he showed lithium intercalation into the 2D material like TiS2, MoS2 and so on, and good enough. So he was working in Cambridge, and so he developed lithium cobalt oxide, okay, LiCoO₂. Okay, this was the first material in 1980, and then he showed lithium intercalation actually, and then. So in between we have Professor Samar Basu. He was not a professor that time. He was working in the Bell Lab. He showed lithium intercalation into graphite, into the anode. Okay, and later there is a faculty called Professor Rachid Azmi. He also showed lithium intercalation to graphite. So he was a professor at the end of his life at IIT Kharagpur, and there's no more. And he was working in the Bell Lab. 1976 he showed lithium intercalation to graphite. And this guy, Professor Yakira Yasuno, so he was a student of maybe he was working as a scientist with Professor Shirakawa. I do not know how many of you know. He is a conducting polymer Nobel Prize winner in 2002. Okay, so this guy was testing lithium intercalation into polyacetylene. Okay, then when he saw this lithium cobalt oxide has been done by good enough, and graphite has been done, so he combined graphite versus lithium cobalt oxide in 1990 and got the first lithium-ion cell in 1991 by Sony, and commercialized since then. And we have been using in some cells lithium cobalt oxide. This is how the first lithium-ion cell came, and then not much development have happened in the cathode or the electrode material side. I'll come to that in the next slide. So this is how it has evolved, and today you see the cathode is I have the real cathode. I have here, you see here, this is what real cathode used in a lithium-ion cell. This is the real anode used in lithium-ion cell. What you see here, this is the cathode material is coated onto aluminum foil. What is that? It could be, you see here, it could be lithium iron phosphate or lithium metal oxide. What is metal? It is a cobalt substituted. We do not use cobalt anymore because cobalt is expensive. So we use a cobalt substitute that is called nickel manganese cobalt. Okay, I'll come to that actually. Then you have a various percentage of nickel, cobalt, manganese. That's I'm going to talk today. I'm going to talk cobalt less. So cobalt was 1 mole in lithium cobalt oxide. Okay, now what I'm going to talk today, point 1. So you see here, this is the lithium. This is the source of lithium. Okay, I told pure lithium is not used. So what is the other side? Graphite is used. So when you charge it, lithium from here. So what is this materials actually? Either this is NMC811 is mixed with some binder and carbon black. Carbon black improve the conductivity, and then they coated onto this, and then calendar, and this is what you see in the real pouch cells actually. Okay, and what you see here is a carbon, which is a graphite carbon, graphite. Okay, is a So what is the electrolyte? Is another key important factor is called alkyl carbonate in LiPF6. LiPF6 is stable till 4.5 volt. Alkyl carbonates are stable till 5.1 volt. again, Electrolyte is another lecture, I can give on electrolytes itself. So ECDC or ECDMC is a diethyl carbonate or dimethyl carbonate, general mixture of all the three are generally used as a solvents with the LiPF6. LiPF6 is the best salt today for the lithium-ion battery. Okay, again, speaking as they say, the properties can be spoken even in a class. So what I want to tell you, during charge, lithium from this lithium cobalt oxide or lithium iron phosphate goes and intercalate between the carbon sheet of the graphite, the graphene sheet of carbon, and during discharge it come back to the parent compound. That's why it's called, it's hop between the cathode to anode. That's why we tell it's a rocking chair mechanism. Okay, this is one lithium ion is moving between. So how fast lithium ion you can move, then you tell is a fast charging material. Okay, so we'll come to that to some extent. So you see here, and I just even want to tell you, so you see here aluminum, here you see copper. Why it is so? Aluminum is stable at higher voltages like real 5.5 volt, and if you go 0.6 volt and less, 0.76 volt and less, you will have aluminum. Lithium will alloy with the aluminum, so you cannot use for other anodes. Whereas this is stable till 3 volt. The copper is stable till 3 volt and low voltages. So that's why copper is a good current collector for the anode side, and this is a good current collector for the cathode side. And which one? Aluminum. And you will see that again, lot of things can be told even here. Aluminum is thicker. When you work, you will see aluminum is thicker because and copper is thinner. Copper conductivity is almost twice as aluminum. That's why it is make thinner and thicker. Okay, so and we use a separator. This is a real separator. This polyethylene polypropylene tri-layer separator we have been using. I do not know, this is not the polyethylene separator. This is some other separator. Somehow I think missed. You can see whatever is there here inside is a polyethylene polypropylene tri-layer separator. What you see, the white one is a polyethylene polypropylene tri-layer separator. It consists of 15 layers of electrodes, cathode, anode. All the cathodes connected in parallel and all anodes are connected in parallel. When you connect in parallel, you increase the energy. When you connect in series, you increase the voltage. Remember it. You want to increase the voltage, you have to connect them in series. You have to connect them in parallel. That means all positive together, all negative together, you increase the energy or capacity. Clear, my friends? So this is how the amount of lithium you intercalate, that determines the capacity. The metal ion determines the voltage. Remember always, the metal ion determines the voltage, and the amount of lithium you intercalate, that gives you the capacity. So just want to brief what the start of today, okay, and then we'll go to our research topic. So I told you lithium cobalt oxide was in 1990, and then 2007-8 lithium iron phosphate came. This was invented by Akshay Padi, which is from Odisha, and this fellow Nanjunaswamy from Tamil Nadu. His PhD, he was a PhD and postdoc student of Good Enough, and whereas Nanjunaswamy was a PhD from ISC and a postdoc with Good Enough. More than 28 faculty, I want to tell you, from 28 scientists from India worked with Good Enough, including my professors and several of my seniors, maybe 4 or 5 of my seniors worked with Good Enough even. Okay, so what I will tell, so lithium iron phosphate, what you see is a contribution of two of our Indian scientists. The graphite anode, what you see is also a contribution from Indian scientist Samar Basu. Okay, then it has realized that cobalt is only limited to Congo, and Congo has child labors and mining issues. It's all taken by China and many things. So what it has been believed, so people started and it has become expensive. I do not have a chart today. So cobalt price is very expensive than your lithium even. So even sometimes people tell you can invest on cobalt rather than in gold and platinum even. That's the price is going that high actually. If you at least use cobalt, then it will be very expensive. So that's why today we talk about no cobalt. Okay, so that's why people started with lithium, nickel, manganese, cobalt. So I'll just write one formula, then you can understand then you'll so the parent compound is lithium, sorry, I don't know. Oh, this is working. So lithium cobalt oxide, okay, and this I replace with a nickel, manganese, cobalt, okay. Sorry. So initially it started 1/3 O2. So it's called NMC333 or NMC111. Then it is a lithium, nickel, 0.5 manganese, 0.3 cobalt, 0.2 O2. It's called NMC532. Then lithium, nickel, 0.6 manganese, 0.3 cobalt, 0.2 O2 is called NMC622. Then lithium, nickel, 0.8 manganese, 0.1 cobalt, 0.1 O2, this is called NMC811. So today we have reached almost this one that I am going to talk what are the issues. So with increase in nickel, we will get more capacity but less thermal stability. I'll have a slide, I'll talk about that. So this is the interest today actually. So because this you can get more energy from the NMC, not LFP. This is another chemistry what I told you, lithium iron phosphate. So lithium iron phosphate has voltage of 3.3 volt, whereas this material has voltage of 3.7 volt. I'm talking about the operating voltage. Okay, so this material has 3.7 volt, whereas lithium iron phosphate is 3.3 volt. So energy will be much higher in case of this material. So you get a 250 watt-hour per kilogram if you get a cell, whereas here you can get around 170 to 200, maximum 200 watt-hour per kilogram. So today we are talking about NMC811, or people also talk about lithium sulfur batteries. People want to use lithium. I told you lithium has high capacity. You want to use sulfur, it is also one of the abundant element. And if you see the capacity of sulfur is 1675 milliampere hour per gram. Okay, and so on. So again, lithium air is free. And if you combine, lithium with the oxygen, it's like your fuel cell. Like you can get 11.65 watt-hour per kilogram, kilowatt-hour per kilogram actually. Close to your ICE engine, 14 kilowatt-hour per kilogram, which is ICE engine. Correct? Then people talk about solid-state batteries. Again, this is another area where you can prepare. People talk about quasi-solid state, which is gel-based electrolyte. People talk about solid-state electrolytes where you have the same cathode, anode, and you have electrolyte is solid-state electrolyte, which is coming up. You need a special technology to fabricate the solid-state batteries. And the chemistry remains same. You have NMC, you have LFP, you have graphite, you have silicon. This all remains same. And then we talk about the future. Then I'll talk about dual ion batteries, dual carbon versus carbon, no metal ions. It's very interesting, correct? And the voltage is 1 volt higher. Is a different area that you can speak. People also talk about multivalent, correct? Calcium, magnesium, zinc, they talk about, and this could be future. I'm not talking about they won't come. Lithium, nobody, next 10 years, nobody can beat lithium. Sodium-ion batteries could come in the next 5 years. Sodium-ion battery have come in Japan and China to some extent. It is in a trial. So India also will be getting sodium-ion batteries in the next 5 years. So. Then recycling lithium batteries is one of the important area. When you talk about lithium-ion batteries, you see, I have listed a lithium iron phosphate. There is a doping of iron with manganese. You can get, this is lithium, sorry, Li is removed, lithium manganese iron phosphate. Even you can get more energy. I'll come to that. And then lithium nickel manganese oxide spinel. This is a high voltage cathode. You can work, but it's not easy to, it is a 4.7 volt cathode. I told you lithium-ion battery operate at 4.3 volt. If you have a electrolyte, you can use this material at 4.7 volt. You have to operate till 4.9. Develop a electrolyte which can operate till 4.9. You have a cell which is 4.7. You have a 3.7 versus 4.7. You think of the energy. Energy will be significantly higher than the NMC or LFP cathodes. And thus I told, solid localized, you just see solid localized, they are stable till beyond 5 volt. Only what is the issue? With the interface is one of the issue, conductivity is another issue. Correct? If you can solve these problems, you can have a good solid localized. And the target today is to get, if you want to drive an aeroplane, you need 700 watt-hour per kilogram, not 250 watt-hour per kilogram. Okay? And let's see how one can develop the lithium-ion battery cathodes and anodes. So what we do actually, basically we prepare nanoparticles. Where nano will have fast diffusion of ions. You see this is the pomegranate kind of structure where primary particles are nano, secondary particle is micro. So you want to increase the tap density, otherwise it will be voluminous. You know, your lithium-ion battery will be voluminous. So you need to increase the tap density. To make this, you have to make a micron size particle. And so these battery materials are not conducting. So we make a electron conducting layer on the surface, and sometimes we do a lithium conducting layer on the surface to improve the interfacial stability at a high voltages. And as already I told you, doping can improve the electrochemical performance by improving the structural stability of the material, basically. So the goal is always the charge, improve the capacity and the voltage, so that improve the energy actually. Another way what people try to do, structural battery. They remove completely the aluminum and copper. They use a 3D based electrode architecture where the material are impregnated to the matrix. This is a 3D electrode architecture where you don't need a PVDA binder, which is organic binder, which is insulating. You don't need, but you need a carbon binder to bind the carbon with the carbon, and they are very flexible. Okay, and so you can make, but it is done at high temperature again. So the these fibers have a conductivity 1 order magnitude lesser than this aluminum. So it has been tested. Many people, there is a couple of companies also working in this area where you can have a flexible structural battery, and energy density could increase, not significantly high, it will be 10% can be increased. And advantage is that the interfacial contact, you know, where here you have a 2D, here you have a 3D, so that you have fast diffusion of lithium ions or fast charging. So what generally people do, actually we do little coin cell level, you know, people do, and I have some coin cells parts, you know, you can see the latter, you know, so this is generally the study level, you know, this is the bottom part, this is the top part of the coin cells. So that's we make in the lab, and then once succeeded, we make a full cell. Most of the data is presented in the paper here. So very rare people present here. This is TR level 3, 4, and then we go to the POWSA itself, that what I showed here, and then for a high capacity, always the industry is required, you know, to roll out bigger cells. So let's come to, this is what I wanted to speak. Let's talk about why the low cobalt or no cobalt based electrode materials. Already told you, cobalt is expensive and is only limited to Congo, and Congo mines are taken by China, and Congo has a lot of political issues and child labor and so on. So that's why you see here, whatever I've written here, this is all here, NMC 333 or NMC 111. So it is reduced. So you see here, nickel content is increased, manganese, so manganese content reduced, cobalt content is reduced. So why, you can ask me, sir, why nickel, manganese, cobalt? I kept a slide for you, maybe you can see, maybe, you know. So nickel gives you, when pure phase nickel is very difficult to synthesize, you will have lot of impurity, and so but nickel will give you the capacity, cobalt will give you structural stability and conductivity, manganese gave chemical stability. That's why very essential. But too much manganese, what will happen? You know, all know the general distortion, correct? Manganese will undergo disproportionate reaction, so that leads to the structural transition, which is not good. Structural transition in the lithium-ion battery is not at all good for the health of battery. Okay, so you see here what I try to tell. So you have now NMC 811. Okay, so we have increased the nickel content, reduced the cobalt content. So if you see here, so you can increase the capacity by increasing the nickel content, and you can see here capacity retention, that like the charge to discharge. Suppose first cycle, 100 cycle, 200 cycle, like today, after a few months, after 6 months, one cycle is one charge and one discharge. That's what you are talking, and then you are charging the cell phone in the night, so you have like completed almost, when you talk, it is completed one cycle. One charge, one discharge is called one cycle. So how long you can do the charge discharge? Correct? You are doing almost like 80% depth of discharge. That means when 20% charge is there, you are charging your cell phone. Most of the you are charging at that point, or the 30%. So depth of discharge is like kind of 20%. In EVs it is different. The EVs operate between 40 to 80%. Okay, so that life will be better. If you do deep discharge, your battery is going to damage very soon. Deep discharge, fast rate, low temperature, these are the premature, your battery will fail prematurely. Okay, you will have lithium dendrite formation also here. Even though you are not using pure lithium, you will have also lithium dendrite. At low temperature, fast charging will cause the premature failures. So anyway, so what I want to tell you, so capacity retention is lesser when you go to the like 100% nickel, and you can see a thermal stability, you know. So phosphates are more stable than oxides, because oxygen can be released easily from the lithium NMCs, whereas phosphates you have a strong PO4 bond actually. So phosphates, that's why lithium iron phosphate, what you see in the two-wheelers is mostly LiFeP PO4. NMCs are now used by MG vehicles, and you will find they are NMCs, so they have high energy. Now also Nexon also, Tata also started with the NMC chemistry. It's like possibly this is a 532 or 622. Okay, this is what you used in your EVs today. Okay, and if you go here, then what will happen? Your capacity is increased, your energy is increased. Okay, but thermal stability will be reduced. Already I told you, nickel gives capacity, cobalt gives structural stability, manganese gives chemical stability. Okay. So the first work I want to talk about, this is again a PhD thesis. You know what I'm going to show the 5-7 slides just to explain like how the NMC 811 problem can be solved. I don't want to go into details. The materials are synthesized by co-precipitation method, and so you see NMC 811 is the same structure of this, the lithium cobalt oxide, which is hexagonal lattice structure with the R3 bar M symmetry, and you can see the voltage is very similar to lithium cobalt oxide. You can get 3.7 operating voltage. The nominal voltage will be around 3.7 volt, which is average voltage. Okay, but I told you when you increase the nickel content, so what happens? So you have a formation of so there is a student from Lakshmipur, Assam, you know, so she just submitted thesis on only one material. Some 6-7 papers on this. I'm going to present only 3 of his papers, her papers. So she worked on this. She joined as an Inspire Fellow, and I told her first find out what are the issues with it. Even though proposal was written, I told her find out what are the issues. She told her residual lithium compound. What is that? So you have formation of this kind of compound, Li2O, LiOH, lithium carbon. I'll come to that in the next slide. So if you have this kind of compound in material, you synthesize the material, you store there in your battery room, and then this kind of material surface will be formed. So what will happen? So when you make these electrodes, sometimes the material will be coming out from the electrode surface, because PVDF will depolymerize if you have this kind of species. And then what will happen when you charge discharge, you will have oxygen evolution, which is not good. And so what will, again, you'll have a lithium nickel mixing. You see atomic radii, they will be very identical, so there will be a possibility of a cation mixing. So cation mixing will cause structural change, which is again not required. Okay. So irreversible layer to the spinel or rock transition, we will have also, transition metals also dissolve in the electrolyte. Electrolyte is another, main culprit in the lithium-ion cell. So you will see you have a cracking of secondary particles. That the mid-ball type structure I showed you, you have a cracking. You can see really, I'll show you the same image. So all this cause impedance and the premature battery failure. You will see that how the performance of the cells in this. So why these residual lithium compounds are found? Generally what we do actually, for 1 mole of lithium, we take 1.1 mole of lithium for the synthesis to compensate the lithium loss in the synthesis. So the unreacted lithium on the surface can react with the atmosphere, can form lithium hydroxide, lithium bicarbonate, lithium carbonate. So these salts will cause the failure. So how they form? So then they will react with nickel, can form the NiO kind of rock salt. If you see lithium carbonate, lithium hydroxide, and so on. So this will inhibit, I told you, this will PBDA binder will depolymerize. You may not be able to coat even with the material, and then a significant loss of then you will have lithium-ion mobility also will be reduced, and then which increase the storage cost. So what people do, people either wash it, people do a hydrophobic surface on the surface. So when you do a hydrophobic the coating on the surface, then the residual lithium compounds are buried underneath of the coating, correct? So that's the people do. Sometimes some people do ultrasonic treatment, but still it is not a useful technique, and some people do a secondary calcination to that can be removed, but it will be energy consuming. So what I told the students, can you convert this surface coating? See, this you have the formation of residual lithium compound. The structure is like meatball. On the surface you have a coating of residual lithium compound. Can you convert this LiOH, Li2O, Li2CO3 to LiF, Li3PO4, Li this kind of species? Because you know that LiPo, lithium phosphorus oxynitride, Li3, which is a derivative from the Li3PO4, is a good solid ion conductor, and conductivity of 10 to the power minus 6 Siemens per centimeter meter, and then you have the stability is still 6 volt for this. Lithium fluoride is a mechanical protector, and then you have this lithium base, this boron this fluoride kind of species can reduce the side reactions when you have this thing. So I told her, can you convert it? So she went and then find out. She started with a process, room temperature process inside the glow box. So it was LiPF6 and LiBO, lithium bis oxalate borate, is used as electrolyte additive, and LiPF6 is a salt. He told, can I use this salt of 0.5% and 0.5% LiBO? She just mix and heat at 450 degrees centigrade, not high temperature, just for 10 hours, and then she got the material. So what I'll be telling, the converted material is called so you see, when you have LiPF6 you have this kind of species, LiF, Li3PO4. When you have a LiBO, you have LiBO derived interface. There is no RLC. Okay, I'll show you even, so that's why I tell this is a uncoated, this is a coated. And you see, when you have you take XRD, I don't want to go details of all the three, I'll explain one. So uncoated to coated, there is no change in structure. Okay, because you have just 1% of this material. So most importantly, how we confirm. So this is your RLC, which is like 10-20 nanometer on the surface. When you have converted one, you see you have Li3PO4, which is clearly see from the lattice fringes. That's you can tell I have a conversion of Li3PO4 or this kind of space. So also you can see XPS is a good technique to understand about the surface. The first top of 5 to 10 nanometer can be analyzed by XPS. So when you do charge discharge, you have a very similar capacity. This is for the uncoated one. You have a spike because of the residual lithium compound, and you can see here this is the impedance. So this is more impedance you find for the uncoated one. The coated one you have lesser impedance, the charge transfer resistance and omega resistance, and you see the cycle life. One charge, I told you, one charge, one discharge, one cycle. That's very important for battery application. We have just shown here 200 or 300 cycles. Generally we do many materials, we do 1000 cycles. I'll show you actually, as it was like towards concept of like improving the capacity, just showed 300 cycles. So you see almost 70% or 80% capacity retention at the end of 300 cycle charge discharge cycles, whereas the uncoated lost capacity. Then the student told, sir, this is not this was a IRFA project, still running. So the student told, Sir, it is very difficult to scale up because everything has to be done inside the glow box for the coating and all things. So then she come up with idea, sir, can I make a phosphate interface like MnPO4 and with Li3PO4 by coating Mn3PO4. I told her, go ahead. So then again, the results was very promising, and all the details you can find in the paper, and you can see it reduces the impedance. The cycle stability is 66% at the end of 500 cycles, and whereas this is a pristine material which is only 31%. Again, impedance is reduced. Coulombic efficiency, the discharge to the charge capacity, which is very important, it should be 100%. According to there is a famous scientist who runs Tesla, is called Professor Jeff Dan. He will tell 99.9997. Okay, so it should be 100% reversible if you have a good battery. Okay, so here you see here 99.7%, the Coulombic efficiency is 99.7%, whereas the pristine one is 98.5%. So it improves the Coulombic efficiency as well. Then the student told, sir, still I want to convert completely not phosphate. This is lithium, not lithium manganese oxide and lithium manganese phosphate or Li3PO4, completely a lithium conducting surface. So like Li3PO4 and LiPO3. So why it is very important? I told you in the beginning. So LiPON, lithium phosphorus oxynitride, which is a derivative of Li3PO4, a good solid electrolyte. You see today. So it was invented one by supervisor, Professor Nancy Dudney at Oak Ridge National in 1990. And today a lot of people work in this. And the solid-state batteries have come based on this electrolyte. So she told, sir, can I convert to Li3PO4 and LiPO3? And both are stable at high voltages and they have very good oxygen retention. I told her, go ahead. So she took ammonium hydrogen phosphate and coated onto the material. I have not shown the synthesis. You can go and see the synthesis. Maybe I do not know which paper. This paper. Okay. So XRD doesn't change. You see there is no change in crystal structure from pristine to the LPO, the coated one. And you see you have this is solid-state NMR, this is in the XPS. Solid-state NMR, you can see clearly that 9.8 ppm belongs to Li3PO4 and this 10.9 belongs to LiPO3, and XPS also clearly indicates LiPO3 and Li3PO4 phases on the surface. Completely converting lithium carbonate, lithium hydroxide, lithium oxide to this kind of phases. And this can be clearly seen. RLC, you see the pristine material, and you see you have a clearly indicated Li3PO4, LiPO3 in the TM. You can see the lattice fringes clearly indicates that it's crystalline, and you have this conversion of this materials actually. And our goal is always electrochemistry, battery application. So if you look at the battery, so like the coated one improves the performance, and you see there is another problem. The coated one, the uncoated one have a significant loss of capacity, the voltage drop. So you see the loss of capacity, voltage drop, that means a loss of energy. So area under the peak give you the energy. Remember my friends, this is the capacity into the voltage is your energy. If you integrate this area is your energy. You can roughly calculate the energy by, if you know the average voltage into the capacity is your energy as well. Okay, you have origin or Excel, you can integrate the area, you can get energy of this cell. And you see here is a plot. Here you have a significant loss of the capacity, the voltage drop, and the capacity loss. Here you have significantly less. And then XPS also clearly shows that you have a formation of all LiXPO, LiF, and this kind of species completely even after cycling, and the impedance also not increased much, it is much smaller. And then most importantly, again the postmortem XRD shows that you have a less cation mixing. How you know from XRD you know the cation mixing? The most intense peak, this is I003 peak, this is I10 intensity of 104 peak. So if you divide this, it will give you the value which is close to 1 means you have cation mixing. I told you cation mixing is not good, which will create the structural change in the material. The structural change will spoil the battery. So 1.6 means there is not much structural change. And we have also calculated the impedance. From the impedance we calculate the diffusion coefficient, and so we found also the diffusion coefficient of lithium ion in the coated material is more than twice than the pristine material. This is because of you have LiXPOY interface on the surface. And again, this is a simple charge discharge curve, which is done dq by dV, derivative of charge to the voltage. And you can see here, this shows that you have a reduced structural transition during a cycling. And you can see here, this is 1C rate cycling. 1C refers to the capacity in 1 hour. You do a 1 hour charge, 1 hour discharge. See, generally batteries are, your cell phone are done 1C rate charge, 1C rate charging. Okay, there are EVs today who talk about 30-minute charging. So that means C by 2. So, 2C. Okay, C by 2 means 2 hours. C by 5 means your batteries are charged in the night for 10 hours. C by 10. Okay, it's like that. So here you see 5C, that means 12 minutes fast charging. So this material supposed fast charging. And you see the pristine material, you see you have cracking, whereas the coated material you do not have cracking. So it solves the purpose, and we are trying to scale up this material. If you see the summary of all the 3 works, what I try to speak, first I went with LiPF6 and LiBO coating. It was the results are very promising, but the thing is that, and it reduces the polarization, which I didn't show properly, and it reduces the structural transition. If you look at the paper, it reduces the structural transition. So that means it is good, but the problem is that LiPF6 and LiBO are very expensive, and operation has to be done in inert atmosphere. When you talk about manganese, this kind of interface by using manganese, the phosphate coating is also very good, and the completely conversion to Li3PO4 and LiPO3 we find is fast charging, and this we are scaling up this material for the IRFA project. And so the student has recently submitted the thesis and waiting for the bio-voice examination. So next 15 minutes, so can I go another 15 minutes? Okay, so I'll try to complete. So I'll talk about another new material. So it's called Spinel cathodes. So I was talking about low cobalt. Now I'm going to cover no cobalt. You see here? These are the next generation cathodes for the lithium-ion batteries. So just I won't go results. I just wanted to show you. If you want to do research, you can do this. So this is the parent compound is LiMn2O4. You have 25% of manganese substitution with nickel. So the advantage that you have 37.5% nickel, less nickel than NMC811 is cobalt-free, and you can get more energy because the voltage is 4.7 volt. The disadvantage with the manganese oxide spinel is the general distortion. All manganese oxide spinels will undergo general distortion, and that leads to structural transition. And also the manganese, so it happens because of manganese is dissolved in the electrolyte also. So it's not good for the health of battery. So that's why these batteries are not very common. But some people are still using. The Nissan Leaf came with those who are about Nissan Leaf. Nissan was the pioneer to make electric vehicles in 2010. Okay, and you see they use LiMn2O4, 4 volt, and if you make this material, it is 4.7 volt. I'll come to that. So when you see this material, you have a ordered, you have a disordered one. Okay, disordered spinel and ordered spinel. Lot of work has been done in ordered spinel. So you take a lithium precursor, you take manganese precursor, and then you heat it for 24 hours at 1000 degrees centigrade. You can get LiMn2O4 ordered. Very simple approach, which my professor has done in 2005, 6, 7, something like that. Okay, so but then I told you we do not want a manganese dissolution. So it has been found that can you make a disordered spinel, so where you have some amount of manganese 3+, so that you can achieve you don't have structural transitions. So we have found the composition lithium, nickel, manganese, 3+ and 4+. This composition is very good actually, and I'll come to that actually. This is next time if you call me, I'll give a talk only manganese oxide spinel. So So this is the, you have D48, this is the disorder LNMO, this is order LMO. So we found, see, this is close to your nickel 0.5, manganese, close to manganese 1.5 O4. So the cycle capacity retention is less. We want more capacity retention, okay? And so this is a disorder LMO, okay? You can see here nickel, manganese, this manganese 4 plus, and then O4, and this has good capacity retention. I'll just tell you another important thing here. So this is the material we have chosen, and so if you see literature, I took from the literature called advanced functional material. So we found, that making digital LNMO is not easy. So they do lot of heating and cooling steps to get the lithium nickel manganese oxide spinel. You see, this is the literature I have taken here. So now my student followed a very similar way. They found a two-step like two-step heating and two-step cooling to get even in one shot, not like taking out, doing all things. You see, not like this. They prepared digital LNMO 48. And they found to be very good. I'll tell you even temperature. They went 750, 800, 850, 900, and they found 800 found to be very good. With increase in content with the temperature, they found that you have impurity phases, not to bother much. Just wanted to tell you and they also control the morphologies. This again, we can speak a lot about this. With different morphology, control morphology, you can have different capacity, different loading and energy as well. Okay, that's another topic. I do not want to go details. So what we find, this is, you see here, this is all those who are electrochemists, they project from the 0 to 130, so it looks straight. It is 132 to the range is 132 to 120, so that's why it shows there is a loss in capacity. But if the loss is 3% at the end of how much 200 cycles, here you can see 10% at the end of 600 cycles. That sounds to be very good actually. So we are scaling up this material also as well and filing a patent, and a lot of work we are trying to do, like neutron diffraction and other things, to understand about the structure, how it is helping, the digital LNMO is helping. The paper may be coming out in few months from now. So this is another important area where you can focus. But again, another issue will come, the Electrolyte, because you see here what voltage we are operating. You see, you are operating close to 5 volt with the same Electrolyte. We are using some additive. That is not always useful. If you have an Electrolyte which is operated till 5 volt, you can make this batteries very useful for various applications. And you calculate the energy will be close to 700 watt-hour per kilogram for the material itself, and you can get more energy than the NMC 811. Okay, 3.7 volt versus 4.7 volt. You have 1 volt surplus. Okay, only capacity here is 180 versus here is 140. Okay, so next, another interesting material, lithium manganese iron phosphate. This is the counterpart of lithium iron phosphate. So this, I was a postdoc at Bar Ilan University, Israel. So we developed this material, manganese phosphate, and followed by manganese iron phosphate. Nobody looked at that time actually, because you have lithium iron phosphate. So we filed the patent, I think Toshiba or somebody took it that time, and I do not know the history. But today it is told that this is the next generation cathode metal. Nobody worked for 15 days. You can see the work. You just put my name, it will come. The first paper will come here. So this is a lithium manganese iron phosphate. Is one of the fastest material. Is a orthorhombic structure. But issue here is that you have to make nano. You have to have a carbon coating like lithium iron phosphate. Same. You have to make a carbon coating. That's very important. If you do not make a carbon coating, it's not going to work. So I'll just show you my data. So this was done again in a very simple way. You mix all the reactants and even carbon black, and do the ball milling and heat at 520 degrees centigrade under argon hydrogen mixture for 3 hours. You get carbon coated lithium manganese iron phosphate. I didn't put carbon here. So you can put carbon. This is a carbon coated lithium manganese iron phosphate. So you can get actually very easy approach. By using those process, we have synthesized even during the time 20 kilogram. Industry worked 20 kilogram. And today, I told you, these are the companies, even the Amara battery, one of the leading battery manufacturer in India is Amara batteries on the latest battery. So they are trying to get Gosen Technology, who is the leader in lithium manganese iron phosphate. So they are going to get this battery technology. So batteries will be lighter. So if you look at the performance, so this is we are getting around 140 milliampere per gram, and at 20C, that is 3-minute charge discharge, even you can get close to 100. It's very good. And you can see here, this was a 6% carbon coating, high surface area carbon coating onto lithium manganese iron phosphate gives 90% capacity tension after the end of 1,000 charge discharge cycles. It's wonderful again. So, and this was my 2019 data, Angu came, and now the Journal of Electrochemicals is the same thing. What we find, the high rate performance has improved. Fast charging has been improved significantly. Next, the path. I'll talk about a new concept called dual carbon battery. What I try to tell, the cathodes, where you have NMC811, I told LNMO, I talk LMFP briefly. I'll talk about now carbon-carbon battery. No cobalt, no manganese, no nickel. Okay. So if you look at both the chemistries, one is lithium-ion battery, one is dual carbon battery. What is the difference? Both are same. You see, you have lithium cobalt oxide, graphite, with LiPF6, the Electrolyte. And here, both sides, you take a graphite. You take both sides are graphite. No transition metals, and only graphite. The anode can be used as an active material for the cathode and anode. So what happens at a certain potential? You are charging around 4.8 volt, the LiPF6 will dissociate as the Li plus and PF6 anion. So PF6 anion will interconnect to the graphene sheet of carbon, and Li plus will interconnect to the graphene sheet to the graphene sheet of carbon at the anode side, and one is at the cathode side. So this is called the PF6 intercalation capacity. There is no. This is a PF6. It is dominated by PF6 intercalation capacity. So you see here, you get close to 5 volt. You have intercalation. Okay. So now we coined this as a scissor cutting mechanism, because both the ions in the electrolyte are intercalating at certain potential. So there we had a rocking chair. Here we have a scissor cutting mechanism. So the advantage is, like if you see, you are not using manganese, cobalt, nickel. You are using a battery out of carbon. It's completely sustainable. You just put into the smelter. Great. You can recycle. Great. And you don't have to depend on any country for the raw material. Carbon can be available in India as well. It is very sustainable, recyclable, and to some extent low cost. But I'll show you the electrochemical performance. The charge discharge cycling is not very impressive. So we developed this. This was during COVID. So the graphite versus graphite cell. We tried with even carbon fiber based architecture. So you see here, this is carbon fiber, and you get this is a full cell, 4.6 volt. You see lithium iron phosphate, 3.3 versus 4.6. You get more than 1.5 volt more. But you see our capacity is less, 70 milliampere per gram. If you have the best carbon, if you can produce. In regular, if you see from the graphite, you can get only 42 milliampere per gram actually. But we have here developed till 70 milliampere per gram. You see, the charge discharge cycling, I told it should be stable. It should not be declining. So what you see is decreasing. And here also you see at 5.2 volt is decreased. That is not good actually. So the problem is that the electrolyte is the source of ion here, lithium ion or PF6 ion. So once it drains out, so you don't have the capacity. It is not very stable. You remember, for a loss of Li plus, you will have also a loss of PF6 anion as well. Okay, it has to be counterbalanced. The domino effect also plays important role. So so what people are trying, why LiPF6? You can have also different anions like fluorosulfonamides, tetrafluorosulfonamides, or BF4 anions. This is what is used in aluminum ion batteries, aluminum per Cl4 minus, or even what recent times we have done a lot of work, maybe 3-4 papers on this. So where we have added linear solvent or fluorinated additives to go high voltages, or even high concentration. I'll show you a data in the last slide. 5 molar instead of 1 molar, high concentrated. If you take, it is very stable. But the goal is cheaper. If you use high concentration of 5 molar LiPF6, it's not going to be cheaper. Okay, so also in the recent times we have tried recycling graphite electrodes can improve the performance as well. So we have taken, we have carefully removed the SCI layer which is formed in the graphite electrode and used, and you see the commercial graphite can give you 45 to 50, whereas now the recycled one can give you close to 70. So that means you have a kind of advantage of around like 50 to 70, which is a kind of 25 to 30% added capacity. So I have turned to a little bit towards graphite. I'm going to finish in next 5 minutes. So we also started thinking of can you do the room temperature, generally what people do at a high temperature, or to recover the metal ions. So what we try to do at pH 9, we can also recover this graphite, and then this is aquathermal regeneration of graphite. So this guy, so we tried with a pH 9, just a slightly alkaline solution, and did aquathermal so that the SCI can be removed and can be used as a good electrode material for this lithium-ion batteries as well as the dual carbon batteries. So if you look at it, he has also compared. I do not have a chart here. Even if you look at the paper, you can see the price chart. Everything is there. He has compared with the commercial graphite. You can also get pure 100% pure lithium carbonate from the graphite electrode that he has recovered. And then the performance, if you look, the performance is very similar to your. This is the regenerated graphite. Is very similar. You see there is a fast cycle irreversible capacitor loss, very important. When you get your lithium-ion batteries, that is already done. So if you see, it is very similar actually. Whether it is a commercial material or our material is very similar, and the cycle stability also is very good. Even our material, regenerated graphite, is much better than the commercial graphite as well. It's on the top, you can see at high rates. And cyclability, if you see, also is quite good and is comparable. We published this work I think last July or something like July, and then also we graphite is produced at 3000 degrees centigrade. It takes 7 days, and they do a spheroidization. It is a cost effective is a very expensive process. So what we try to do now in the recent times, we do catalytic graphite, low temperature, 1500 centigrade. So the student did from the sugar, can take even hard carbons, can you catalyze and do a low temperature graphitic carbon. And we study also the performances in dual carbon and dual carbon batteries and lithium-ion cells. So he did with using nickel catalyst, and you can see the purity of carbon what he has prepared. So we did also Indian patent, also a publication. You can see, the impurity is very less, the surface area is very comparable, and the particle size also very similar, and the thermal stability also very, very, very good. So this, I don't want to go again. Electrochemical performance. The electrochemical performance is on par with the graphite electrode. That's what I want to show in this slide. And what I want to summarize in this area is that this is very promising. Carbon. A battery comes out of carbon. It was not new. In 1842, it was shown in 1942. In 1942, it was shown in sulfuric acid, H+ ion and sulfate ion. And we did this work in 2012 when I started when I was in Krishna's lab, and after coming I started after 2020. And so this is also a good area where electrolyte plays an important role. Of course, graphite, you need to have a good graphite where you can have high capacity. We have even gone to 110 milliampere per gram, but still the data is not published. And I showed you, you see, he has taken 5 molar lithium fluorosulfonamide with 2 molar LiPF6, and he made a 4-layer pouch cell and is very, very stable. It is possible. It's not that it's not possible, but I told it's cost effective. I don't think it is cost effective. When I'm using 4 molar LiFSI and 2 molar LiPF6, which lithium-ion battery uses only 1 molar LiPF6. So, but it's a sustainable approach, very reliable and safe, and the cost also could be reduced if you will work out in this aspect. For lithium, you can use the same thing for the sodium-ion batteries. Instead of lithium salt, you can use sodium salt. But again, remember, the dynamics plays important role. The way lithium can move, sodium doesn't move. You know, so sodium doesn't interconnect in the graphite. It interconnects to the hard carbon. Again, you have to play another way, like how to improve all the things actually. So sorry. What I try to speak today, I try to give a brief overview of lithium-ion batteries, the technologies, the current status today, and then we talk about how we can develop the cathodes in our laboratories and which area you can work, and then we talk about mostly NMC 811 based cathodes, and then mostly how we can improve the performance by mitigating the RLC to a value-added layer. That's what we tell adverse to beneficial, converting RLC into a lithium conducting layer. And I told you digital LNMO is very good. If you can make digital LNMO, I think that's also a very fascinating aspects of lithium iron, lithium nickel manganese oxide, spinel cathodes, and lithium manganese. This is going to play in this will be coming up in a year or two. This material, and this material needs electrolyte. And dual carbon batteries are beginner approach, but again electrolyte plays an important role for the development of this kind of batteries. So I've come close to the end of my talk. So with this, I would like to thank first, I do not forget my supervisors, who Professor A.K. Shukla from IITG, who taught me the aqueous electrochemistry, Professor Daron Orbach, who taught me non-aqueous electrochemistry, and then I independently work with them at Oak Ridge National Lab and see the path to develop the solid oxide conductors and the first solid state battery in the world today with John Bates and Nancy Dodney. You know, they developed in 1990 the solid state batteries. I worked with them, and I thank my collaborators and my student who contributed significantly to my growth, and I thank you for your kind attention and welcome for any questions.
Has taken away valuable learning that will shape our futures, careers and research pursuit. On behalf of IIT Guwahati SPE student chapter, I extend our heartfelt thanks to Professor Martha sir for sharing his valuable time and his vast experience with us. I also thank all the members, all the research scholars, students present here for participating, for making this seminar a great success. With this, we conclude today's seminar. So after the event, we will be sharing a feedback form. So please, I hope that everyone please fill the form, right? So thank you all for attending this, and you may take the refreshment which is provided outside. Thank you.